Hello and welcome to my presentation on the bioconjugation of filamentous phage Pf1 to a polyethylene terephthalate degrading enzyme. My name is Brad. So everyone is familiar with plastic. It covers our food, it's in our takeout containers, and of course, as biochemists, we love to use thousands of these plastic microcentrifuge tubes to do our research. But one place plastic has no right being is in the oceans. Plastic pollution, especially in the oceans and waterways, will be one of the biggest problems that my generation and generations to come will have to solve. And unfortunately, the current state of plastic pollution in the world's oceans has reached an all-time high. A study in 2014 found that there is 5 trillion plastic particles in the ocean that weigh cumulatively over 250,000 tons. And here's a sobering figure showing the density of various sized plastic particles in the ocean. And you can see that the density of plastic particles is high throughout all the world's oceans. And thus, there exists the acute need to develop techniques that can remove plastic from the world's oceans. And so one major type of plastic that will be the focus of this talk is polyethylene terephthalate, or PET plastic, as I'll refer to it for the rest of this presentation. And we are all familiar with PET plastic, as it's the plastic that goes into plastic water bottles. PET is classified as a thermoplastic, and it can be readily molded into shapes that are incredibly useful for various purposes. And if we had the power to look under a microscope and see the molecular structure of PET, it would look something like this. It will consist of polymers of ethylene terephthalate that form long polymeric chains that can be wound into fibers. And what these fibers do is they allow for a stronger system. But unfortunately, the stronger and more lightweight system leads to a more environmentally persistent and less resistant to degradation plastic. And so how can our generation hope to degrade such a persistent organic pollutant? And well, the answer may lie in nature's chemical machinery found in microorganisms and nanotechnology. Unsurprisingly, give nature enough time to adapt and you can observe some amazing chemistry, and actually chemistry that can degrade PET. And these are PET degrading enzymes, and numerous enzymes of this fashion have actually been discovered. But one enzyme has persisted through the literature as one of the most efficient enzymes currently available to degrade PET. And this enzyme is humanicola inoculant cutinase, or HIC as I'll refer to it. HIC is a naturally occurring enzyme found in soft rot fungus that normally acts as a cutinase, which degrades a plant cuticle. And a commercial preparation of this enzyme exists and was actually bought for the purpose of research during my 494. So here's a chimera model that I made of HIC, and what it highlights is the surface exposed lysine, shown in green, as well as the catalytic triad, shown in red. And what I really want you to focus on is the catalytic groove, shown here in red in the top kind of right end of this structure. And this is where all the magic happens, and it allows bigger molecules to slip and fit right into there. So this molecule, again, is HIC. And so now that we have nature's chemistry, what about the nanotechnology? And let me introduce you to filamentous phage Pf1. This phage is a commercially available bacteriophage that affects Pseudomonads bacteria, and it's 2 nanometers long, consisting of 7,400 copies of a major coat protein called P8. And Pf1 is an absolutely massive biomolecule, weighing 34.3 times 10 to the 6 Daltons. The major coat protein on the Pf1 has solvent-available reactive amino acids that can be modified, as was proven by previous research done by myself and other members of the Honeck laboratory. And really, the best way to imagine what Pf1 looks like is like a corn on the cob, where the corn kernels are copies of the major sheath protein. And filamentous phage are much like an industrial steel beam, in that you can weld many things to it. And the biochemists in Dr. Honeck's laboratory are a lot like welders, using our knowledge to chemically weld interesting molecules to the surface to add functionality. And so this brings me to the goal of my project. And the goal of my project is to create a plastic degrading Pf1 HIC scaffold, whereby the HIC is actually chemically and covalently linked to the Pf1 surface through the major sheath protein. And to do this, a chemical linker system was developed. and this utilizes bioconjugation techniques. The major undertaking of this project was to actually chemically link HIC to Pf1, and to do this, the following linker system was developed. And there was 3 bioconjugation reactions. In the first bioconjugation reaction, a solvent-exposed lysine on HIC surface was reacted with Trout's reagent. And essentially what this does is it installs a nucleophilic thiol. In the second reaction, the major coat protein P8's N-terminal lysine was reacted with the maleimide Peg4 NHS ester. And what this yielded is a P8 linked to a maleimide through a spacer PEG chain. And what this does is essentially adds length away from the Pf1 surface. In the final reaction, the maleimide on the Pf1 coprotein was reacted with a nucleophilic thiol on HIC. And this is what actually links the 2 systems together. So now we have a covalent linkage. And the reaction between a nucleophilic thiol and a maleimide is well known in the literature and occurs readily under mild conditions. And so that's why we chose this system to make the linker. So you may be asking the question, well, how was the products confirmed? And the products were confirmed by an enzyme assay to be later discussed, as well as 2 forms of mass spectrometry, MALDI-TOF mass spectrometry and ESI-MS mass spectrometry. And unfortunately, due to the time constraints, I won't be able to delve into how these amazing techniques work, but they are amazing and they do work. Now that the introduction has been explained thoroughly, we can finally get into the results section. The first reaction to take place was the modification of HIC with the Trout's reagent. I want to first note that all the reactions that were conducted were taken place in thiol purification buffer, or TPB buffer as I'll refer to it. This buffer consists of sodium chloride, sodium phosphate, as well as EDTA, and was titrated to a pH of 7.2. So in this first reaction, unmodified HIC was reacted with a 12-fold excess of Trout's reagent, or 2-aminothiolane. The reaction took place at room temperature for 1 hour, and the product was purified by a 10 kilodalton spin filter. And here is the following mass spectrum obtained from the purified product. And what you can see is that there is a mass peak at 20,447. Now, HIC unmodified has a mass of about 20,362. And with the addition of a Trout's reagent, you'd expect about 102.04 daltons to be added. The reason you don't exactly see the perfect mass peak is because MALDI-TOF can't resolve peaks down to within 1 or even a few daltons, and so the mass will be somewhat off. And you may ask the question, well, why not just use ESI-MS? And the reason for this is because simply HIC will not fly in ESI-MS. But the mass spectrum still does prove that HIC was indeed thiolated. The second reaction to take place was reacting the nucleophilic N-terminal lysine of the major coat protein P8 with the maleimide DPEG NHS ester in a roughly 50-fold excess. The reaction took place in TPB buffer at pH 7.2 at room temperature for 2 hours, and the product was once again purified by use of a 10 kilodalton spin filter. Now, the unmodified P8 has a molecular mass of about 4,606, and with the addition of the DPEG4 linker as well as the maleimide, you'd expect a additional mass adduct of about 400 daltons. And this is exactly what we see here. The only difference being also the addition of methanols, or formic acid. And methanol and formic acid was used to get the protein to fly in positive mode of ESI-MS. And this is the spectrum obtained from the ESI-MS positive mode experiment. So before I go any further, I must talk about a major hurdle in my project, and that's the fact that HIC is an incredibly sticky molecule. Not only have I worked with HIC, but a previous master's student also worked with HIC. And what we found is that HIC likes to non-covalently bind to different surfaces. We found it will bind to glass, it will bind to plastic, and most importantly, it'll bind to biomolecules such as the Pf1 scaffold. And this is really important because I want to make a covalent linkage. And what this will do is will be a non-covalent linkage and will give me false positives. And thus, I must use an equally sticky biomolecule to block all the non-specific binding sites. And of course, every biochemist's favorite sticky biomolecule is bovine serum albumin, or BSA. And this was used to block all non-specific sites on Pf1 by using a 1% BSA solution. And so this is what I picture the system to now look like. So now I was finally able to create the functionalized nanomaterial using a roughly 800-fold excess of the major coat protein maleimide to the thiolated Hic with an unspecified amount of BSA. This reaction took place in TPB buffer at pH 7.2 for 2 hours at room temperature, and instead, this time the product was purified by use of a 100 kilodalton spin filter. And this is what I picture the system to now look like. It is the Pf1 with non-specific binding sites blocked by BSA, with maleimides exposed on the surface, as well as Hic being bound to the maleimides through the thiolation. And how was I able to actually determine if the reaction did indeed work? Well, Pf1 Hic cannot fly in neither ESI or MALDI-TOF. But what we can do is use an enzyme activity assay to indirectly measure the presence of the Pf1 Hic scaffold. And this was exactly done. So the chromatogenic reagent PNPB was used, and once hydrolyzed by Hic, it turns into this product, which can have its absorbance measured at 347 nanometers. And through the magic of mathematics, you can actually obtain the enzyme activity. And this is exactly what was done. And this is the second buffer used in these experiments, which is a sodium phosphate buffer. And this is the enzyme assay buffer. Using this enzyme assay, I was able to construct a Michaelis-Menten curve for the Pf1 Hic BSA scaffold, but this time I used a 5-buffer system. And what do I mean by this? Well, in the first half of my Chem 494, I had actually synthesized the Pf1 Hic scaffold using all the same steps that were mentioned before, except I used a 5-buffer system. And this semester, I wanted to make this process a lot more streamlined and simpler to do, so I changed to a 2-buffer system using just thiol purification buffer and the enzyme assay buffer. But due to the unfortunate COVID-19 situation, I was unable to actually construct the Pf1 Hic scaffold using the 2-buffer system. So the only results I have was using the previous 5-buffer system. But the results still prove what I was trying to show, and that is that the Pf1 Hic scaffold has a much higher activity than that of the control. So the control in this experiment was to use the exact same synthetic process, except to use unthiolated Hic. And so theoretically, once the final reaction occurs between unthiolated Hic and the Pf1 maleimide, any unthiolated Hic should just fall right through the spin filter because it can't covalently link. But we know, of course, that Hic is sticky, so it did stick a little, which is why we still have some activity from the control. But we found a Vmax about 30 times higher than that of the control and a Km of 3 times higher. And so this reaction did indeed work. And so my proposed future work is to synthesize the Pf1 Hic scaffold using the 2-buffer system as mentioned on the last slide. I would also really like to obtain a Michaelis-Menten curve for a direct comparison of the Pf1 Hic scaffold to Hic. And this would tell me how well the Pf1 Hic scaffold can degrade plastic relative to the same stoichiometric amount of Hic. And lastly, I would really like to use a method such as pegylation to add a coat around Hic, preventing non-specific binding. And this would really help in one of my major hurdles of my project. So thank you so much for listening to my presentation. I hope you enjoyed it. And I would like to personally thank Dr. John Honeck for his continued support in my academic as well as my personal chemistry career. I would also like to thank other members of the Honeck Laboratory, Taylor Urquhart, Jameson Pfeiffer, Maya Lopendic, and Fatima Mirza for their help during my research project. And again, I just want to thank Dr. Honeck for always encouraging me as well as the other Honic laboratory members to make nanomaterials. Thank you very much, and I hope you stay happy and safe during this strange COVID situation.